I'm a bit of a gearhead, so I hold this near and dear to my heart. It's a great company, and they've been taking very good use, making very good use of the simulation in their processes. The typical 3D design process that they used to use is, create a 3D CAD model, build a physical prototype, and then physically test performance. And then, from there, you need to iterate until your requirements are achieved. Now, when building a prototype is going to take a week to a month, iterations can be drastically slowed down. In an integrated simulation process, we are able to iterate and optimize and then build one prototype and validate via simulation. And if we have issues with that prototype, we've already kind of dissected our problem and we know a lot more about the potential issues we have. And if we do need to go back to the drawing board, we can further optimize. We're going to still be much further ahead than the time lag involved in creating physical prototypes. So the old process, as this slide shows, is that as information is low early in the concept and design prototype phases, risk is high. But if we can move our iteration and learning process earlier in the design cycle, our information is going to increase and our risk is going to decrease. So what does this all look like? Well, here's an example of one of Forge Line Racing's wheels that we've worked with them on. And you'll see that we have multiple load cases at the bottom of the screen. We're starting out with a worst case cornering loads. Then we're looking at the vibration sensitivity or frequency analysis of the wheel. Then we move into an optimization phase that uses both of these simulations. And then once we find an optimum design, we want to make sure that, okay, we didn't bend it, but during repeated loading, are we going to break it? So let's take a little closer look at this simulation. And you'll see that we have a feature manager tree for simulation at our left. And our parts are defined and their material properties. And then we have interaction between our different components defined via what we call contact sets. This could also be bolts, pins, and idealized connectors, welds, for example. And then as we move down, we see that we have a fixture where we're grabbing the inside of the wheel by the inner bead. Because this is on a test fixture, the pseudo hub that we have on here is only allowed to move up and down. And then we also see that we have a force applied to our hub, and this mimics the test machine pretty closely. And at the bottom of our simulation, so we're kind of working top to bottom, we can see that we get our stress results, displacement results, and a factor of safety. So we can display our stress results on this particular wheel, and we're trying to keep our stresses under 5,000 psi. And we can look at our stresses in multiple ways. We can slice and dice with section clippings if we want to see what's going on inside. We can also use things such as ISO plotting or clipping to display only stresses above or below or between a certain range, so we can really get a feel for how is the loading occurring in this wheel, where do we need to add and remove material. Take a peek at a displacement plot, and if we want specific values in certain locations, we can go in here and start probing our model and get values at distinct locations. You can plot those so we can get a feel for the range of values we're looking at, and even save these out as a sensor. And sensors are something, as you're going to see, are critical to being able to do design optimizations. It's the feedback loop for the simulation. And then lastly, a very handy way of looking at results are in terms of factor of safety. How are my stresses normalized to the material strength? So we see in this current optimized version of the wheel, we've got a factor of safety of 1.6 for this particular load. Now, this was a stress analysis, which most everybody thinks of when they think of FEA. But in addition, most products, there is a aspect where we are concerned about frequency of vibration. And The great thing about SOLIDWORKS simulation is that everything that is over here in the frequency analysis can be drag and drop from the stress analysis. So the forces, the fixturing, as you see, I can grab these and drag them over to another analysis. And in this case, frequency analysis are going to show us the resonance frequencies of the structure. So how does this wheel like to vibrate? Our goal for this particular wheel is to keep this first mode of vibration over 300 hertz. So we've done one stress analysis, we've done one frequency analysis. But the reality is that we need to iterate to be able to find optimum designs. And I mentioned earlier, sensors, and these are giving us, you might have used these in SOLIDWORKS CAD before, but in addition, sensors can also be used to track simulation data. So I can add a sensor to the model, look at mass properties, simulation data, stresses, the maximum over the model, or I can choose to look at the maximum or minimum values over specific entities at the part level or even down to the individual face, for example. But also, how do I make this model change? I'm going to use my SOLIDWORKS CAD parameters. They could be from features, or they could be from in a sketch. And in this case, you see that we have two angles that are defined, that define geometry. And if we want to add another reference, we can just display our annotations. So we have already defined is this angle, which is essentially going to drive the thickness of the spokes. And then also, we have another angle dimension that's going to drive essentially the vertical height of the spoke. And if I wanted to add another parameter, all I have to do is just give it a name and then select a feature dimension, and now it's linked. So what I'm going to be able to do is use these parameters to drive a design optimization. Let's go over into the optimization mode, and we can see here that we have a run that was already, a set of runs that were already completed, and part of our inputs are the range for our parameters, and then we have constraints. In this case, the stress analysis must produce results of stresses less than 5120 psi, and the frequency analysis must provide results greater than 300 hertz. So we're running two different types of analysis here. We could also run multiple stress analysis, both a cornering load and, let's say, a worst case curb event, for example, and they could have different limits and different sensors. Our goal in this case, big thing with motorsports, is decreasing the unsprung mass, or the amount of weight hanging off of the suspension. So in this case, we're asking the optimization to minimize the overall mass of the wheel. So when we take a look at our results, I can plot my specific results, such as frequency or stress. And this is our initial iteration for the wheel. And we see that our spokes are thicker. And we can see these stress results on the model, in addition to investigating the max values and values for our parameters. And so this is our initial design. And we look at, we are almost 27 pounds, or 26.2 pounds, so 26. And then our optimal design that we verified, that we're going to verify for fatigue, and we're down to 24.7 pounds, and we're meeting our frequency and our stress targets. And as we walk across the results table from the optimization, we can view the different scenarios that we tried, and in this case, we can see this column is red, meaning that we failed, and in this case, our frequency was too low and our stress was too high. And we can see here that our spokes are getting pretty thin. We can go back to our optimal design, because we're going to run this in fatigue analysis. So we let the model reset. So, what is fatigue? Well, fatigue is essentially, I didn't bend it, but am I going to break it? And then the inputs to fatigue are the number of cycles. So in this case, if I want to add an event, I could add multiple events and sum up multiple analysis. We see here that I have an opportunity to put in the number of cycles, and then I pick the stress analysis that I'm using to define that event. So we've already done that, and we've defined our material properties for the fatigue analysis. And what we see for a fatigue result is what we call damage. And essentially, 100% damage equals a very high probability of developing surface cracking in the model. So we see here that our legend is set for 100%, and we don't see any red in the model, so we've met our stress, our frequency, and finally our fatigue requirements.